So with this, we will formally start the program. So just one quick announcement, as many of you would have seen in the schedule, this first week we have a series of pedagogical lectures. We also have posters which has to be put up. You all would have received an email on that. So please do put up the posters. And this evening we have these flash talks of posters where you can just in 1 minute introduce your posters, right? So please do send your poster slides to Varghese by 2 p.m. today. With that, the first inauguration lecture, Professor Alessandro Morbidelli. All of you might have heard of the NISER model. You know, he's the world expert on how our solar system formed and ended up in what we have in the system. I will not take much time, so let's start with the lecture series. Professor Morbidelli.
Thank you.
Each of the lectures we have allotted 1.5 hours, but feel free to ask questions. We have enough time in between also during the session to ask questions. So please keep it as interactive as you want.
Okay, thank you. Can you hear me? I think yes. Okay, thanks for the invitation. It's an honor to be here to this school. I'm impressed by the infrastructure, the quality of this room, really world class. So, okay. So I've been asked to give 2 lectures. The first one will be about the migration of planets in protoplanetary disks. And the second one tomorrow will be about the effect of this migration on the orbital architecture of planetary system, capturing resonance, formation of resonance chains, global instability. Let's start from the very fundamentals, why planets should migrate in disks. Okay, the key point is that if we embed a planet in a disk, the planet perturbs the distribution of gas in the disk. So if initially you have a disk with a uniform density, which is represented here by this uniform blue color, the moment you insert the planet in the disk the planet creates a spiral wave where the gas density is enhanced. You see here that the color is bright white, which means higher gas density. So this is what we call a spiral density wave. And the generation of this wave is what drives the migration of the planet in general towards the star. So the first question is, why should the planet generate a wave? So first, this wave has a clear pattern. So the disks around the star turn in a Keplerian fashion, so are characterized by what is called the Keplerian shear. So that means that with respect to the motion of the planet, the disk inside the planet rotates faster, and the disk outside the planet rotates more slowly. So in a reference frame co-rotating with the planet, the fluid elements inside the orbit of the planet move this way. The fluid elements outside the orbit of the planet move that way. And so the wave is bended in the direction of the motion of the gas relative to the planet. But why there should be a wave in first place? So it's very simple. You have a planet. Again, we are in a reference frame rotating with the planet. This is the star. This is the radial direction. This is the azimuthal direction. So the planet is fixed. You have a fluid element, say, in the little bit in the outer disk. So relative to the planet, this fluid element comes in vertically in a circular orbit. So it moves this way with a relative velocity with respect to the planet, which we call VRL. And because of the encounter with the planet and the gravity of the planet, the orbit of the fluid element is bended. So the way it works during an encounter is that the bending does not change the relative velocity vector, just rotates the relative velocity. This velocity is the same as this velocity in absolute magnitude, but it is rotated, which means that now it has a radial component that it didn't have before, and the azimuthal component is necessarily reduced with respect to the initial one, because the full vector is the same, but now we have a radial component. So this means that this encounter has created a change in the azimuthal velocity of the fluid element directed in this direction, which means that the fluid element is accelerated along its orbit, receives a positive force. And if you accelerate something in orbit, what happens? Happens that it goes out. And so as a result of this encounter, the fluid element trajectory is bended, it's accelerated, and then it has to go out, and it goes out further at a larger distance from the star than its initial distance when it came in. So it gains a distance delta R. And this is true. You can check it in hydrodynamical simulations. So this is again a radial direction, azimuthal direction in a frame co-rotating with the planet. And this is what is called the streamline, so the trajectory of a fluid element in the disk. So it comes in, it's accelerated by the planet, it dives towards the planet, goes out. Here, this is the delta R that I described before. And then the internal forces of the disk, viscosity and pressure, bring it back to the original location because the streamlines in the disk are closed. But what is important to note is this deflection of the fluid element due to the encounter with the planet. As a result of this deflection, you have a compression of the gas, which creates an overdensity here where the streamlines are bent from this sketch. And this overdensity then propagates radially as a pressure wave at the speed of sound, because the way gas communicates with itself is through pressure. And so all density perturbations propagate as pressure waves at the sound speed. And so this is the radial propagation of this compression that the gas suffers. But at the same time, the gas is also in rotation relative to the planet because it's in the outer disk. And this is what generates the wave. So it's a combination of the radial propagation and the radial speed of the overdensity created by the encounter with the planet with the Keplerian shear. And this is what gives the wave. And now that we have understood why the wave is generated, we can try to understand why planet migrate. So the effect of the planet is to break the axisymmetric symmetry, the axial symmetry of the disk, because now we have this wave which acts as an overdensity. So let's consider first. Before we go, so let's see first the wave. So this is a disk with a uniform density. We inject the planet in the simulation, and you see that the planet generates the waves. The planet rotates around the star, and the wave, which is launched by the planet, moves at the same time as the planet around the star. Why we say that the wave is in co-rotation with the planet around the star. And this means that if we go in a rotating reference frame so that the planet is fixed, we don't see it turning around the star anymore, then the wave is stationary in a rotating reference frame. So now we are armed to try to understand why the planet has to migrate. So as I said, the planet breaks the axial symmetry in the disk because there is this overdensity which doesn't have an axial symmetry. So let's consider first the outer part of the disk, so the disk beyond the location of the planet. What does the planet see? Rather uniform disk plus an overdensity, which is here. An overdensity by gravity exerts a force on the planet, right? Because the density, the wave trails the planet, the force that this wave will exert, this overdensity will exert on the planet is a force directed like this. So it's a force that opposes to the motion of the planet around the star, so exerts a negative torque on the planet, which means it slows the planet down and tend to, well, if it slows the planet down, the planet will lose energy and angular momentum and will spiral towards the star. But then we have the inner disk. In the inner disk, it's the opposite, right? The density wave needs the planet, and so the gravitational force that it exerts on the planet will be directed in this direction. So it will push the planet along its orbit, will exert a positive torque on the planet. So we try to accelerate the planet, and if you accelerate the planet, you push it away from the star. So you have two opposite effects. The outer part of the wave is slowing down the planet and forcing inward migration. The inner part of the wave is accelerating the planet and forcing outward migration. So the question is, who wins? And in general, it is the outer wave that wins. And the reason is that the disk is slightly in sub-Keplerian rotation. Because the disk has an internal pressure, it feels a pressure force directed from the sun out, which subtracts from the solar gravity. And so to be in equilibrium on circular orbits around the sun, the gas rotates around the sun a little bit more slowly than the Keplerian speed. So if this were not the case, if the disk were in Keplerian rotation, the dynamics of the gas relative to the planet is here you see the streamlines and the arrow showing the direction of the motion of the gas, will be perfectly symmetric. But even if the disk has a uniform density, it is sub-Keplerian, and so the dynamics that occur is like this. So first, let me show why the disk is sub-Keplerian, because it may not be obvious. Right? The pressure is the product of the sound speed times the density of the disk. And the sound speed is the scale height of the disk squared, sorry, times the density of the disk. And the sound speed is the product of the scale height of the disk times the Keplerian frequency, and rho is the density. Now, the scale height of the disk is more or less proportional to R. Omega is proportional to 1 over R to the power 3/2. So the product of these two is proportional to 1 over R. And if we have a flat disk, so the surface density of the disk is the same at every radius, the density decays as 1 over R because the scale height increases. And so the pressure is typically, even for a flat disk, typically disks are not flat, they also decay. But it's at least like sigma, it's like sigma divided by R squared. And so the pressure gradient is negative from the sun out, and this is why the disk is in sub-Keplerian. So being in sub-Keplerian rotation means that the co-rotation region is made by these streamlines that make a U-turn at the location of the planet. This co-rotation region is not located at the planet location, but is shifted inward. So the disk is moving a little bit more slowly. So to move at the same speed of the planet, you cannot be at the distance of the planet from the star. You have to be a little bit closer to the star. And so at the planet location, there is a net flux of gas that goes in this way. And the gas moving upwards is much further from the planet than the gas moving downwards, which means that the interaction with the planet is much stronger for this gas going downward and for this gas going upward. And so the wave that will be generated by the encounter of these downgoing streamlines will be much stronger than the wave generated by the encounter with the planet with these upstream streamlines. And so this wave will exert a bigger torque, and this exerts a negative torque, so drives the migration of the planet towards the star. So because the overdensity of the wave is proportional to the mass of the planet, because the planet is the perturber, the density of the wave is proportional to the mass of the planet, and to the overall density in the gas. It's a fraction, the overdensity is a fraction of the density of the gas. Then the planet migration speed has to be proportional to these two quantities. So it's migration of a planet is linearly proportional to its own mass, the mass of the disk. So I just said that it's typically inwards because this branch of the wave wins, but then somebody may say, okay, but let's take a steep disk, a disk with a steep surface density profile, like this. Right? And then I will have much higher density inside and outside. And because the torque is proportional to the density of the disk, maybe the inner wave will start to win. But this is not the case because of a process called the pressure buffer. So if you have a disk with a given density as a function of R, Here, this is the location of the planet. The same disk has a given rotation curve. So this is the rotation frequency of the disk as a function of distance. And the location of the planet, the frequency, the Keplerian frequency is this one, because the disk is sub-Keplerian. Once again, at the location of the planet, the disk is rotating less fast, and it's in co-rotation with the planet closer to the star. If I take now a steeper disk, so to enhance the density in the inner part, so to hope that the inner branch of the wave can win, what happens is that the disk becomes even more sub-Keplerian. So the co-rotation region becomes even further from the star, which weakens the inner part of the wave even more. And so at the end, you can make this disk as steep as you want, and you actually never make the inner wave win. On the contrary, the inner wave becomes weaker and weaker as the disk becomes steeper, because the disk becomes more and more sub-Keplerian. And the co-rotation region is shifted. So, and indeed, one can demonstrate that the net torque on the planet, which is negative, okay, it becomes even more negative with increasing alpha, and alpha is the power law here of the surface density distribution. So the steeper is the disk, the higher is alpha, the more negative is the torque. So it's the opposite of what one would naively expect, that the steeper disk, because it has more gas inside, will eventually drive the planet out. Actually, the steeper is the disk, the faster is in your migration. A few things about the properties of the wave. So the wave is an overdensity in the gas. So to create an overdensity, you have to fight the internal pressure of the gas. So the higher is the scale height of the disk, the stronger is the pressure. So the smaller is the overdensity in the wave. And also, the higher is the scale height in the disk, on the aspect ratio, the faster is the sound speed. So that means that in a synodic period, which is a cycle of the wave, the pressure, the overdensity pulse has traveled faster, because it travels at the speed of the sound. And so the wave will be less rapid. And now I will show an animation showing how the wave changes with the aspect ratio of the disk increasing. Of course, a disk has a given aspect ratio. This does not change the aspect ratio. But in a simulation, you have a planet within a given disk, and then you change in the simulation the aspect ratio of the disk to see how the wave changes. And this is how it goes. So as you can see, with increasing aspect ratio of the disk, the wave becomes more and more pale, less pronounced, and it's also much less rapid than it was before. So one can demonstrate that as a consequence, the torque felt by the planet decays with the aspect ratio in the disk. The higher is the aspect ratio, the weaker is the torque, because the weaker is the wave. And it's actually proportional to h over r, so the aspect ratio of the disk, to the power minus 2. So thinner disk exert a faster migration on the planet than thicker disk. So we can summarize this initial part of what is called type 1 migration. Type 1 migration is the theory for planets that perturb the disk, but not enough to change the overall radial density distribution. Yes? Well, as the pressure, the density propagate out by pressure, it tends to be smoothed away by viscosity. And so after, it's a competition between viscosity that tends to spread the disk and the sound speed that tends to propagate out. So in an inviscid disk, the wave goes very far out. In a more viscid disk, you see just the first two. So type 1 migration concerns the planets like those that we have seen that generate a wave but don't open a gap in the disk. And then I will talk about gap opening a bit later. So planet migration, as we said, is proportional to the mass of the planet. That's the main property of type 1 migration. So the bigger is the planet, the faster it moves. It's proportional to the surface density of the disk. The more massive is the disk, the faster the planet moves. But it's also the migration, the speed of migration, it's inverse of the square of the disk aspect ratio. And so this is the general formula, right? The change in specific angular momentum of the planet, the specific angular momentum is the square root of the location of the planet, is the angular momentum per unit mass of the planet. So it's in general negative. So there is this coefficient that becomes stronger and stronger. The steeper is the disk, alpha is the exponent of the power law of the disk, proportional to the mass of the planet. Then you can normalize to the mass of the star. Mass of the star appears squared because you place the disk here for dimensional reasons. It's proportional to h over r to the power -2, so r over h power 2 sigma, and it's proportional to the location of the planet, the power 4, and the frequency, rotation frequency, orbital frequency at the power 2. So it applies only for relatively small planets that don't change the global structure of the disk. And as you can see in this formula, there is no mention of the viscosity. The viscosity matters for the final damping of the wave, but what drives the migration is the interaction between the planet and the beginning of the wave. Gravity, of course, is proportional to 1 over the distance squared. So what matters is the wave close to the planet. So how far the wave can propagate is not really important. It's a second order effect on the migration formula. So in this video, we see nicely an example of migration. So it's in a co-rotating frame with the planet. So you don't see the planet turning around the star, but you see the planet moving. And in this plot, you see the distance of the planet from the star as a function of time as the movie is being played. So as you can see, migration is a fairly linear function. So the planet decays towards the star and relatively quickly. So if you apply the formula I gave before for a planet of 1 Earth mass at 1 AU in a fairly typical disk, what we call the minimum mass solar nebula disk, a reference disk that everybody uses in the community. Doesn't mean that the disk was exactly this one, but it's a good reference. So the density at 1 AU would be 1,007 of gas, 1,700 grams per square centimeter, and the aspect ratio would be 5%. So then the migration time scale would be only 200,000 years. That means that A dot over A is 200, 1 over 200,000. So basically the planet would move towards the star on this time scale. It's very short. The disk's lifetime is of the order of a few million years. So there is ample time for planets already of an Earth mass to lose them into the star if something else happens. If nothing else happens, we'll see later what could be reasons, possibilities to slow down migration or track migration. And because of the formula I gave you, you can use this number and scale it up, right, easily. So for instance, when you wonder what is the migration time scale of a planet that is not 1 Earth mass, but 5 Earth masses, okay, in a disk which is 3 times more massive and twice thicker. Then we know how things scale. So it scales linearly with the mass. So we take our 200,000 years, migration scales linearly with the mass. So we divide by 5. It scales linearly with the disk, and the disk is 3 times more massive. So we divide by 3. But it's inversely proportional to the square of the thickness. The thickness is doubled. So we multiply by 4. Then you take this product and you find 53,000 years. So this is very useful formula, right? So once you remember these numbers, they're very easy to scale to any kind of problem you have. Now, the wave not only forces the planet to migrate towards the star, but it also damps the eccentricity and the inclination. Although we not speak about the inclination, about the eccentricity of the planet. Why is that? So if you have a planet on an eccentric orbit, in a frame co-rotating with the mean orbital speed of the planet, so that your frame makes one revolution, as the planet makes one revolution, your planet is no longer stationary because it's on an eccentric orbit. So your planet will have a radial excursion, but also the azimuthal speed changes. The planet is faster at perihelion and slower at aphelion. So your planet draws an epicycle in this rotating frame like this. It goes faster at perihelion, goes lower at aphelion, and has a radial excursion, so creates this epicycle. And so what happens is that at perihelion, the planet moves faster than the local gas, and at aphelion, it moves more slowly than the local gas. So we can take the same figures as before. So because at perihelion, the planet moves faster than the local gas, the gas at the planet location will move from top down. Okay. And for this reason, as before, the lower part of the branch will be the wave will be much stronger than the upper part of the wave. So that means that the planet is slowed down at perihelion, but at aphelion, we can rotate the figure. The planet is moving faster than it's moving more slowly than the gas. Sorry. So the gas at the location of the planet in the rotating reference frame is moving from bottom up, upwards. And so the wave will become stronger here at the top than here at the bottom. So in this case, there is a positive torque exerted on the planet at aphelion, which speeds the planet up. So we have a body on an eccentric orbit, which is slowed down at perihelion and speeded up at aphelion. This is what we do for space navigation. So what happens in this case, the eccentricity is damped. Slow, because when you are on an eccentric orbit, you move faster at perihelion and slower at aphelion. If you slow down at perihelion and accelerate at aphelion, you recircularize the orbit. And to show that this is what happens, I show the simulation, but I need to stop it, move here. Okay, so here is the disk. And you see my mouse? You see the mouse? Or not? No, apparently you don't see the mouse, so okay. So you see this is the usual density of the disk, this is the planet, and this is the epicycle of the planet, and this is the wave that the planet launches. So look at what happens as the planet goes around its epicycle. Okay, so here it just passed through perihelion, right? And you see where the wave is pronounced behind the planet, as I said. So here the entire gravitational force is pulling the planet back, so it's slowing down the planet at perihelion. And if we wait up in orbit, up, here we go, the planet is at aphelion, and now you see it's like a comet, right? The planet has a tail, and you have this, the strong part of the spiral density wave is directed in this direction, so exert a force that tries to accelerate the planet, or accelerate the planet. So the eccentricity, so this is why the eccentricity is damped. The eccentricity damping is proportional to the velocity of the planet relative to the disk, because of the dynamics that I showed. And so it's proportional to the eccentricity itself. So the decay rate of the eccentricity is proportional to the eccentricity. It's still like before, so it's the intensity of the wave, and so the damping rate is proportional to the mass of the planet and the density of the disk. And it has a stronger sensitivity on the scale height of the disk. It's a little bit complicated to show why it is so. So instead of being proportional to h over r to the power -2, like the torque exerting migration, it's actually proportional to h over r to the power -4. So eccentricity damping is much faster than migration. That's what it means, because h over r is a small number, 2%. So the eccentricity damping is much faster than migration. And so we can write it as E over tau E, and so tau E is the So what we have seen before, the formula I gave before for the change in the specific angular momentum of the planet is still valid, apart from small corrections and eccentricity. So we can say, can apply the same formula to the change in angular momentum of the disk, but because the angular momentum of the planet, but because the angular momentum of the planet depends on the sum major axis and the eccentricity of the planet. The actual damping of the angular momentum, which is given by the formula I gave before, it's actually a combination of the A damping and the E damping. And the E damping is given here. The angular momentum damping was given by the formula I gave before. And so the change in semi-major axis is actually given by this. So it's the usual rate in case the planet is circular. But if the planet is eccentric, there is this term that makes the semi-major axis decay even faster. And this is very important for the resonant dynamics that we will see tomorrow. And it's the key of a process that we call overstability of mean motion resonance. So when a planet is eccentric, it decays towards the planet faster, but the eccentricity decays also extremely faster. Then the planet circularizes and migrates towards the star at the usual speed. Now, all I've said so far concerns planets that are small enough not to change the global structure of the disk. That is, they create this wave, but the density, overall density in the disk remains the same. But this cannot be true forever. If the planets are massive enough, they have to exert a stronger effect on the disk. Why? Because we've seen before that the wave, which is an overdensity in the disk, exerts a gravitational force on the planet. But as you know from Newton's principle, there is the action-reaction principle. So if the outer wave exerts a force on the planet exerts the force on the wave. So the planet exerts a force on the wave directed in this way, so exerts a positive torque on the outer disk, and exerts a force on the inner wave directed this way, so tries to slow down the inner disk, exerts a negative torque on the inner disk. So which means that the planet tries to push the outer disk out and to slow down the inner disk, and so to push the inner disk in. Of course, the disk has internal forces due to viscosity, due to pressure, that try to oppose to this force of the planet. But if the planet is big enough, it can overcome the internal forces of the disk, and then a gap can open, because indeed the planet manages to push the outer disk outward and the inner disk inwards, creating a depletion in the gas density along its orbit. This is what we are going to see in this movie. So we are going to see a planet that is inserted in the disk, and initially it's a low mass planet, so it just generates a sort of a wave. But then in the simulation, the planet is grown artificially, okay, fast. So it doesn't last forever in an unphysical way, but just to see the effect. And then you will see that as the planet grows in mass, the global surface density of the disk changes. So here we go. The frame, I think, is a co-rotating frame with the planet. So here it's the planet with its wave, and you see that over time, the gas along the orbit of the planet is being removed. And at the end, so we have a figure which is very different from the one I showed before. We have not only the spiral density wave, but we have this big gap along the planet's orbit. The disk is only present at a given distance from the planet outside. The central region, which is black, it's not physical. It's just that in the hydrodynamical simulation, if you want to go too close to the star, of course, we have numerical issues because the frequency, orbital frequency becomes so fast. So if you want to make any simulation on a meaningful time scale of hundreds of orbits, you have to limit your disk to a patch that doesn't go too close to the star. So this cavity is not physical, it's just a numerical model, so to say that before. But this gap is physical, it's the one that is open. Okay, so can we estimate how big is the gap? in principle, it's easy because we can take our formula for the torque. So it's the same torque that the wave was acting on the planet is acting on the wave. So this is the torque that the planet acts on a disk, on a ring of the disk located at the distance delta from the location of the planet RP. So it's you divide your disk in concentric rings, and for each ring, so it's characterized by a given distance delta, and you compute the torque exerted by the planet through the wave on that ring at distance delta. At the same time, the disk has internal forces, particularly due to viscosity, and so as the surface density tends to change, the disk exerts a torque on itself, which is given by this formula, which then depends on the viscosity. If there is no viscosity on the disk, nothing happens. But it depends on the gradient of the surface density of the disk. The viscosity tends to smooth the disk out and to prevent large gradients of the disk density to be established. So as the planet starts to carve a gap, these gradients become steeper and steeper, right? Because you have a density at the beginning. So with the disk like this, so relatively smooth gradient, but the planet starts to open a gap, and so the gradient becomes very, very high here and here. And so the viscous torque becomes stronger and stronger. So you have a competition. The planet torque tries to push the gas away, but as you push the gas away, makes the gradient steeper, and this enhances the viscous torque. Okay. So at some point, you may hope to reach an equilibrium, and when the viscous torque and the gravitational torque are equal to each other, and so while you do some math, which I will not here will take too long, and you can solve this equation, so this equal to this, for each value of delta, so for each concentric ring in the disk, to compute an equilibrium gap profile of the density as a function of delta, which is the distance from the planet. And this is what has been done, for instance, in this paper in 2004. It works pretty well for disks that have a strong viscosity, and the formula fails when the viscosity is weak, because, of course, if the viscosity is weak, is the coefficient in front, so this torque becomes very weak. And so this formula would predict gigantic gaps, very deep and gigantic gaps for small viscosity, and even infinite gaps for vanishing viscosity, which is not really feasible. What happens is that if the viscosity is weak, so this gradient continuously grows, okay? But at some point, if it grows too much, the disk becomes unstable. To be stable, the disk has to satisfy the Rayleigh condition, which is this one. What is the Rayleigh condition? Is simply the requirement that the radial gradient of the specific angular momentum of the disk is negative. And so basically it means that, yeah, so the radial gradient of the specific angular momentum of the disk has to be positive for the disk to be stable. So that means that the angular momentum of the disk grows in distance from the sun. As soon because this gradient of the specific angular momentum of the disk is linked to the gradient of the density. Right? If the gradient of the density becomes too steep, because there is the torque of the planet which is not counterbalanced by the viscosity, then at some point the gradient of the angular momentum in the disk becomes negative. And then the Rayleigh condition is not valid anymore. The disk becomes unstable. And what does it mean that the disk becomes unstable? Is that the disk develops turbulence, which in practice enhances the viscosity of the disk. So initially you had a non-viscous disk or a low viscosity disk, but if the planet turns it unstable, the disk becomes turbulent and becomes viscous. And so this limits the opening of the gap. So there is a maximum slope that the gap's edge can have, and these are the slopes that are at the limit of the Rayleigh instability, where the slope given by the gradient of the specific angular momentum of the disk being zero. This is the work that has been published by Kanagawa et al. In 2015. And so this is what happens in reality, in a numerical simulation. Take a planet with the mass of Jupiter, and let's study the surface density of the disk around its orbit for various values of the viscosity. So if the viscosity, so this is minus log of the viscosity, so red would be relatively high viscosity, and 7.5 is a very weak viscosity, that is 0 viscosity in China. So you see that this is the gas surface density profile normalized to the initial one. So all effects of gradients have been removed by the normalization. And you see that if the viscosity is high, the gap is relatively shallow. So it's not even a factor of 10. Right? The depletion of the gas at the planet location, even if this planet is Jupiter, because the viscosity is so high, the density is just reduced by a factor of 5. But then if you reduce the viscosity in the simulation, you see that the gap becomes deeper, as expected in Varnier's paper. But then as you decrease the viscosity even further into the limit of the inviscid disk, you see that the gap becomes deeper, a bit wider, but not indefinitely deep and indefinitely wide. There is indeed a limit depth and the limit width of the gap, which is set by the Rayleigh instability. The opening of a gap has a big effect on migration. And this is illustrated in this plot, in this movie. So it's a movie like the one before. So in the rotating frame, we see the planet that migrates. We project the distance as a function of time. The planet at the same time is opening a gap. And so you will see the effect of gap opening as clearly. So go. So the planet initially is moving by type 1 migration. At the same time, it's opening the gap. Now the gap is open, and you see that its migration is still inward, but slows down considerably. So the effect of gap opening slows down migration. Does not block migration, does not reverse migration, but slows down migrations. Giant planets migrate more slowly than small planets. So we have this situation that in type 1 migration, the bigger is the planet, the faster it moves. But this does not go on forever. If the planet is too massive, it starts to open a gap, and then migration slows down. So in some sense, the migration rate as a function of the mass of the planet is something like this, more or less. So this is the type 1 branch. We will see it goes to some migration rate independent of the mass of the planet. I will come to this, the type 2 branch. And this is sort of transition. So why is a planet with a gap forced to move more slowly? The reason is that now we are in a situation like this. The planet has opened a deep gap. If the gap is spurious, just a partial gap, we are in the transition region, which is very messy. Also, we show at the very end. But let's make the case clear. The gap is very deep. So the planet has effectively divided the disk in two, and there is no gas in between. There is an inner disk and there is an outer disk, and the planet is there. So what can the planet do? Okay. The planet is, you could say, well, okay, it wants to move. But if it goes too close to the inner disk, of course, it feels a strong force from the inner disk because it approaches the inner disk. And the inner disk, where the wave is going upwards, gives a positive torque. So the planet cannot approach the inner disk because it will be repelled out. And similarly, the planet cannot go towards the outer disk because the outer disk The wave takes away angular momentum from the planet and moves the planet inwards. So the planet is condemned to be in the middle of the gap, not go into the inner disk or to the outer disk. So that means that if the planet wants to move towards the star, the entire disk has to move towards the star, together with the gap, because the planet cannot move relative to the gap, repelled by the edges of the gap. So at what speed can the gap move towards the star? It can move only at the speed, at the viscous radial speed of the gas, because the disk has some viscosity. The gas is drifting towards the star, is spiraling towards the star. That's why the protoplanetary disks are also called accretion disks. They bring gas to the star. And the radial motion of the gas is equal, it's a famous formula, to minus 3/2 the viscosity mu over r. So this will be the speed at which the gap can move towards the star. The planet is condemned to live in the middle of its gap, prisoner of the gap, created, it put itself in jail. And so the planet migration will be the same as the migration of gas in the disk, will be minus 3/2 mu over r. And this is the famous formula of type 2 migration produced by Bill Ward back in 1997. And what it is important is that in this simple vision of migration, so the migration speed for a massive planet in type 2 becomes independent on the mass of the planet and even independent on the density of the disk. So immediately you understand that this is a sort of asymptotic formula that cannot be absolutely correct, because it makes no sense physically that the migration is independent of the mass of the disk. You have a very thin disk with a negligible mass, and the planet will still move at the same speed. So of course, this formula has some limitations. But in first order, for a massive disk and a massive planet, this is what happens, and it's because the planet is blocked in the gap, and so is locked in the viscous evolution. But if you look a little bit broader, of course, things are a little bit more complicated. This is a result of a series of numerical simulations. I forgot the citations, but a number of people did this from Duffel, Will Cly, our own group, and so on. So this shows the migration rate of the planet normalized to the Keplerian speed, okay, as a function of this quantity. This quantity is the ratio between the mass of the disk interior to the orbit of the planet, sigma rp squared, so about the mass of the disk interior to the orbit of the planet, and the mass of the planet. Basically, it's the ratio between the density in the disk and the mass of the planet. This number a-dimensional multiplied by rp squared. And this is the measured migration rate. And this is the viscous drift rate, the famous minus 3/2 mu over r. So as you can see, the planet does not move exactly at that speed, not too far. In the limit of a massive disk relative to the planet, so the planet is massive to open a gap, but the disk overall has a lot of mass. Indeed, the migration rate does not seem to depend on this quantity, as predicted by the Ward formula. Only depends on viscosity and not on the mass of the planet, nor on sigma. And indeed, we have this sort of asymptotic behavior. This asymptotic behavior, curiously, the migration rate is not exactly the viscous drift rate, it's a factor of 2 higher. And this is because the viscous motion of the outer disk goes a bit faster, because the existence of the gradient of the gap has changed the gradients in the disk. But it's a little change, a little bit. On the other hand, if you go towards the low disk mass, so sigma is small compared to the planet, then of course a light disk cannot move the planet at the same speed. And so you go into this branch where migration is proportional to this ratio and linearly proportional to this ratio. And only the coefficient depends on viscosity. So a viscous disk will have a larger coefficient, so a steeper dependence than a low viscosity disk. But of course, there is this asymptotic branch, and this is called the inertial limit. So a very massive planet in a light disk has to slow down. So for instance, when Jupiter formed, the disk was still massive, was moving fast, but as the gas is removed from the disk, for instance, in photoevaporation, by photoevaporation, the planet has to slow down. Okay, so far so good. So I explained the classic vision of type 1 and type 2 migration. But to have a more complete view of how the planets evolve and be able to understand their resonant dynamics tomorrow, we need to go in a little bit into some complication. So let's go back to small planets, planets that don't open gaps. Okay, so they have gas everywhere, also along their orbit. And because they have gas along their orbit, we need to worry about what the gas along the orbit is doing, which creates a torque, which is called the co-orbital torque that we neglected up to now just by considering the spiral density. So you have a fluid element that shares the same orbit of a planet. And what does this do? It does this kind of motion relative to the planet, again in a rotating frame with the planet. So this is what is called a horseshoe motion, because it draws these curves which look like horseshoe. And what happens is that these elements so vibrate back and forth. And when one element comes here, encounters the planet, and goes from the outer part of the horseshoe to the inside part of the horseshoe, so doing this U-turn, it loses angular momentum, so it gives it to the planet, exerts a positive torque to the planet. But of course, when the opposite occurs, and there is this other U-turn, and the fluid element goes from inside of the horseshoe to the outside of the horseshoe, the fluid element gains angular momentum and takes away angular momentum from the planet. So in principle, you would say, okay, this is equilibrium, and one effect will cancel the other one. Yes, and so to understand that, let's change our coordinates. So let's go from this system of coordinates, which is the polar reference frame with the radius and the azimuth, to this system of coordinates where we introduce simply a radial direction and an azimuthal direction and analyze what happens in these coordinates because it's much more clear. And this is what we get. So this is the radial direction, the azimuthal direction, the star is in that direction, the planet is here, or if you look here, because Mumbai are the same. And these are the horseshoe trajectory. So let's take a fluid element, okay, that makes a U-turn. And this fluid element is characterized by a given delta R in the radial direction and a given delta phi in the azimuthal direction. So there is a theorem in mechanics, it's the Liouville theorem, that says that the canonical volume, which is the product of d phi times dj, where j is the specific angular momentum, is conserved. So in doing this U-turn, this quantity is conserved. Now, in doing this U-turn, d phi is conserved because you have 180 degrees on this side and 180 degrees on this side. You cannot have compression or dilatation in the phi direction. But because the angular momentum, specific angular momentum is the square root of the radius, then a change in radius is equal to the change in angular momentum times the square root of r. So consequently, when moving from r to r prime, okay, because the interval in a specific angular momentum dj is the same, dj must be conserved because d phi must be conserved and the product must be conserved. So the interval of angular momentum in the fluid element is conserved. Then the radial extension of the fluid element has to expand by a factor square root of r prime over r. So this fluid element has the same extension in phi, but is stretched in r by this ratio, square root of r prime over r. On the other hand, the circle is still 2 pi, but we are further from the sun. So in physical units, this circumference is a factor of r prime over r longer than this circumference. So this fluid element already is stretched by a square root of r prime over r, but then you have to distribute it over a longer circumference. So the surface density here is smaller than the surface density of the gas here by a factor r prime over r. Again, r prime is here, r is here, to the power minus 3 half. And this is the key. So during the horseshoe U-turn, the fluid element stretch and their surface density decreases when they go from inside out, or compress and their surface density increases when they go from outside in. And so in other words, this means that if the surface density of the disk across the horseshoe region changes as 1 over r to the power 3 half, then you have the same mass per unit time encountering the planet in this direction or in this direction. And so the torque is new. But if the surface density of the disk across the region is different from 1 over r to the power 3 half, is steeper or shallower, then you have some the effects don't cancel. And in particular, if the density, the disk is steeper, you have more mass doing this U-turn than this U-turn. So that means that the planet is accelerated towards the star. And if the disk is shallower than this, then you have more mass doing this U-turn than this U-turn. And so the planet is actually slowed down. So in particular, if the density gradient is positive, so it's not like 1 over r to the power 3 half, but it's even a positive function of the distance, then this co-orbital torque can become positive and very strong and can win over the negative torque exerted by the spiral density wave. So first of all, is it realistic to have a positive gradient in the disk? It can, because there are regions of the disk, in particularly close to the inner part of the disk, where gas is depleted. It can be depleted by magnetic effect related to the star. It can also be depleted by a change in viscosity, because close to the star, the disk becomes very hot, so it becomes ionized, so it can become magnetorotationally unstable and become very viscous. So you can expect this positive surface gradient of the disk in the inner part of the disk. You can expect them also at the outer edge of a gap of a major planet, which would be here. So you have a Jupiter that creates a gap, another planet that comes and fills this positive gradient, density gradient. So the positive density gradients can exist in the disk. And so they exert this strong co-rotation torque that can stop the planet. And this is a representation of what happens. So the planet migrates inwards, reaches the branch where the region where the surface density of the disk starts to be positive and stops there with some oscillations that I will show in a second. So this is a Cartesian representation of migration of planets of different masses. Each simulation, it's only one planet. It's not all the planets simulated together. So there are no interactions among the planets in a same disk. And you see that the planets all stop at the same location. The location of what we call the planet trap is independent of the mass of the planet. So the planet go there very fast if they are massive, slowly if they have a low mass, because this is the type 1 migration rate, but they all stop at where the surface density of the disk becomes positive enough. And then you have these oscillations that you've seen in the movie as well. And this is because when you have a surface density that is like the one I drew, so with a positive gradient and then a negative gradient, sometimes, in some cases, it's a Rossby unstable. So it creates a vortex near the density maximum. And then you have a gravitational interaction of the planet with the vortex. And this is what is giving this oscillation. There is a caveat, though, that it's true that if I have more gas out than in principle, I have more elements doing this U-turn, so giving a positive torque to the planet than this giving the other U-turn. But by keeping doing this libration, the material should homogenize, right? And at least inside the libration region, we should redistribute the gas, so to achieve the famous 1/r to the power 3/2 surface density gradient that cancels the co-orbital torque. And if this happens, this is called the saturation of the co-orbital torque. So the co-orbital torque is present at the beginning, but after a number of librations, then the surface density in the co-orbital region has been changed to this one, and there is no more co-rotation torque. So the only way the co-rotation torque can continuously exert its effect is that there is something counteracting this saturation. And so you need the internal forces of the disk that establish this positive surface density gradient that can come from magnetic effect, from turbulence, from winds, or whatever. They oppose to the fact that the local surface density across the co-rotation region wants to tilt. And the planet would like to change the surface density into something like this, and you need that the internal forces of the disk prevent the planet from doing so. Only if the disk is strong enough, then the orbital torque is desaturated and continuously acts on the planet. So in an inviscid disk, well, these forces do not exist, and so the rotation torque can be desaturated, but maybe the density gradient is due not to viscosity, but to magnetic fields, and then you can have desaturation by the magnetic fields. I mean, the bottom line is that whatever acts on the disk to create this positive surface density gradient has to be strong enough to prevent the planet from changing the slope in the co-orbital zone. The co-orbital torque is important not only to stop planets at the edges of the disk, but can also change significantly the migration of the planet as they move. And this is called the dynamical co-orbital torque. So I'm trying to illustrate this again in a bunch of movies. So we have again our scheme. This is the radial direction from the sun, the azimuthal direction from 0 to 2 pi. This is the planet, then 0 and 2 pi. And the planet is moving inwards. And look at what happens to this fluid element. Okay? So the fluid element initially will move upwards at a fixed location, because this is what the fluid element does. So it's moving, it's inside the orbit of the planet, so it's moving faster than the planet, so from bottom up, until the planet runs over this fluid element, and then there will be a change in location, radial direction, or in radial distance of the fluid element, and when the fluid element will go beyond the planet, it will start, of course, to move in the other direction because of the Keplerian. Let's see, it's moving up. Ah, here it is, the planet comes. What did the fluid element do? We can maybe show it again. Yes, okay, go. Okay, enters the co-rotation zone, makes a 1 U-turn, and goes out of the co-rotation zone, and it's left behind. So as the planet is moving, these fluid elements encounter the planet only once, are kicked out, so they kick the planet in. So they give a positive feedback to migration. The planet is moving inwards, and the fluid element is kicked outwards, so it pushes the planet even more inwards. So we call a positive feedback on migration. Let's now consider its brother, which is a fluid element, which is just inside the co-rotation region. So this is the boundary of the co-rotation region. And so, as the planet migrates, it moves with the planet. And look what it does. It does a small U-turn here and a large U-turn here. Do it again. Oops. This one we know. Okay. 1 kick and you're out. So positive feedback. Look at this. A small kick at the top, big kick at the bottom. So that means that this fluid element loses angular momentum more here than it gains here. So the net effect of the planet is to give angular momentum. So the fluid element trapped in the co-orbital zone gives a positive torque, so a negative feedback on planet's migration that wants to slow down planet's migration. So we have 2 counter effects. the fluid elements outside of the corrotation torque, as they pass through the corrotation torque, give a positive feedback on migration. Those trapped in the corrotation torque give a negative feedback on migration. So who wins? Again, if the density is uniform across the orbital region, the two effects cancel out. And the positive or negative feedback is only possible if the corrotation region is less dense or more dense than the surrounding disk. But as the planet moves, the situation of the density in the corrotation region versus the density of the in the disk changes, because this corrotation region is moving with the planet, going in another region of the disk, which can be different. So again, during migration, the canonical volume dphi, dj, j being the specific angular momentum of the disk, is constant. But the angular momentum, as the planet moves in, the width for the corrotation region shrinks with r. But there is a relationship between the width in angular momentum and the width in r, which is 1 over r delta r. So if delta r shrinks with r, delta j, the interval, the width in a specific angular momentum of the rotation region, shrinks as square root of r. Okay? And so that means that there is less space for the gas in the corrotation region to stay in the corrotation region as the planet moves. So there is some mass which has to go out of the corrotation region because the corrotation region shrinks. At the same time, the surface area of the corrotation region shrinks like r squared, because the width shrinks like r, but the circumference shrinks like r as well. So you have that the mass trapped in the corrotation region decays as square root of r, decreases by square root of r, but the area on which this mass is distributed decays like r squared. And so the surface density in the orbital region increases like 1 over r to the power 3/2. And this is the key. So if your planet is moving in a disk whose surface density profile is shallower than 1 over r to the power 3/2, then as the planet migrates, at some point, the density in its corrotation region becomes higher than the environment density in the disk. And so the negative feedback from the corrotation region wins, and the planet slows down. And this is illustrated here. So we have a planet, initially at 1, that migrates. And this is the migration rate of the planet, normalized some quantities. And this is what would happen without this dynamical co-orbital torque. So the planet is at 1 and migrates down 2.5, and its migration rate slows down a little bit because it's coming close to the star, but it's still going this way. And now you take into account the corrotation torque. We are in a disk with a flat surface density, so shallow. The disk is constant, and so it's shallower than 1 over r to the power r 3/2. There is no viscosity in the disk, and as you increase your total disk mass, then the effect of this co-orbital torque, dynamical co-orbital torque, becomes stronger and stronger. And as you can see, this slows down the planet. And in particular, if the disk is massive, the planet moves a little bit, but then its migration rate drops to a very small fraction of the initial migration rate. So this is a very effective way to slow down the migration of planets. And but it requires that the disk has a small viscosity, because if the disk is viscous, it tends to oppose to this density contrast, because basically you are in a situation where, so this is the surface density of the disk, and this is the distance. Your planet is here, and because the planet is moving and carrying along its co-orbital region, then the density of the disk would do something like this. And the viscosity doesn't like any steep gradient, so the viscosity will tend to spread the disk and make it more uniform. So this dynamical co-rotation torque works well only in low viscosity disks, and in high viscosity disks, it can be completely neglected because the surface density throughout the co-rotation region maintained at the same level of the environment in the disk. The opposite is true, right? If the disk profile is steeper than 1/r to the power 3/2, migrations can speeds up. Now, disks this steep can be difficult to envision. But if you have a planet that starts to be not really a planet that goes in type 2 migration, but in the transition zone, so where you open a partial gap, and so the migration, the mass in the orbital region is reduced with respect to the mass in the ambient disk, then of course the negative feedback on the orbital region is reduced, and the positive feedback from the non-orbital disk is the same, and so you have a positive feedback on migration. And this is what happens for planets. So this is the distance of the planets as a function of time for planets of different masses. So they have deeper and deeper gaps. And at some point, you can go into a runaway migration, where migration even accelerates exponentially. And this happens when the mass deficit in the orbital region, so the mass that is missing in the partial gap. So now we are in a situation like this. So this is the distance from the planet. So this is the disk, okay? And because there is a planet here, there is a partial gap, okay? When the mass missing here with respect to the disk is large, so this is called the mass deficit, is larger than the mass of the planet, then you enter into this runaway mode, because the faster migrates the planet, the faster is the positive torque exerted by the fluid elements that pass from one side to the other of the co-rotation region. And so you have this extremely fast. Okay, in the last few minutes, I will show you another strange effect that can happen in disks. And this concerns the case where you have two planets opening gaps, a little bit like Jupiter and Saturn. And this is relevant for our solar system, as we will see tomorrow. So let's see what happens first by looking at a simulation. A first simulation done in 2001, simulating at the same time the migration of not one planet by two. In the years 2000, simulations, hydrodynamical simulations were still complicated, and people to understand what happened was just simulating one planet at a time. Massey Snellgrove, to my knowledge, for the first time, put two planets in the disk. And so they had the interactions of the planet with the disk and the planet with themselves. And they chose two masses like Jupiter and Saturn. And they put them random distances, put Jupiter at 1 in normalized coordinates, they put Saturn twice as far. They simulated, and that's what happens. Jupiter migrates inwards in type 2 migration. Saturn migrates initially inwards, then it has this runaway migration that we've seen before, because Saturn opens a gap, but not super deep gap. So it's not really in type 2 migration, it's more a transition planet, so which has a gap, which can be have a mass deficit bigger than the mass of Saturn itself. And so it goes into this runaway migration. And but at the end, here it crosses a resonance with Jupiter, a 1-2 resonance, which breaks and makes the planet temporally eccentric, so breaks this accelerated migration mode. This is not so important. And eventually the planet enters in resonance, the 3-2 resonance with Jupiter. We will talk about resonance capture tomorrow, so we'll not go into that. But notice that once Saturn becomes close enough to Jupiter and eventually it is captured in resonance, Jupiter migration stops and even reverses a little bit. And so this is a way, the first way that was ever pointed out, in which planets may stop migrating towards the star. And this simulations was done in a disk with a large aspect ratio, so a disk with high temperature. If you reduce the temperature in the disk, so you reduce the scale height of the disk, the aspect ratio of the disk, the same happens, but the outward migration of the planet is even more pronounced. And then this, of course, it's intriguing for our solar system history and become really important. So it's been studied by a number of people with different codes, and everybody found this. This is true effect. Why do we have the true effect? Well, first, let's see what is the surface density of the disk when Jupiter and Saturn join each other in this 3-2 resonance. So 3-2 resonance happens when Jupiter makes 3 or revolutions around the star in the time that Saturn makes 2 revolutions around the star. And so this is a plot. The high density is in red, the low density is in deep blue. So you see the inner disk, you see the outer disk, you see that the gap of Jupiter, Saturn is sitting at the edge of the gap of Jupiter. Their spiral density waves merge. The gap of Jupiter is not very clean, right? Compared to the animations I showed before where Jupiter was alone. You see that there is purple inside the gap. So the gap is not very deep. So the situation is clearly complicated. But we can sketch it a little bit to see what happens. So when you have Jupiter and Saturn, the surface density of gas in the disk looks like this. Not a sketch, comes from the simulation, actually. So Jupiter is more massive and opens a deep gap, right? Saturn is less massive and opens a partial gap. And at some point, the planets are close enough that the 2 gaps overlap. So we have this common asymmetric strange feature. So first, this strange feature ensures that the gas can pass from the outer disk into the inner disk. Because Jupiter would like to make his gap deeper, so would like to take this gas and remove it. But this amount of gas is the depth of the gap that Saturn can sustain. So as Jupiter removes this gas, well, new gas comes into Saturn's gap because Saturn is not too strong. And so it cannot sustain by itself a deep gap. So there is a continuous flow from the outer disk into the gap of Saturn because Jupiter is stealing the gas from Saturn and pushing it into the inner part of the disk. So this allows a channel of gas going from the outer disk into the inner disk. And this is why the gap of Jupiter is not very deep, as we also saw before, because there is a continuous passage of gas through the wakes into the inner part of the disk. And so the inner part of the disk does not get depleted because of this refill of gas from the outside. And so this means that the planets are not locked in the gap anymore, because the gas can pass from one side to the common gap to the other. So this is the first key point. The second key point is the torque balance. Now, for Jupiter is a massive inner disk that tends to push the Jupiter out, and a partially depleted outer disk that tends to push Jupiter in. But because this is partially depleted, of course, the inner disk wins, and Jupiter tends to be pushed out. For Saturn, it's the opposite. Saturn sees a massive outer disk outside and basically no disk inside because there is the gap of Jupiter. So Saturn wants to go in. So Jupiter and Saturn are pushed by this common gap in opposite direction. And they do converge until they go in resonance. And once they are in resonance, and they are locked in resonance, they cannot move. They can only move together in order to preserve their period ratio. So they have to decide who wins. And who wins is Jupiter, because it's more massive than Saturn, exerts a stronger wave, and so in principle tends to migrate out, feels a stronger positive torque than Saturn. So in principle, it's Jupiter that wins. But it depends actually on the depth of Saturn gaps. So that's why you have this dependence of H over R. If H over R, the disk is thin, the gap of Saturn is relatively deep. And so really Jupiter feels a strong imbalance and wants to go out and takes Saturn with it. But if you have a hot disk, then the gap of Saturn is very shallow. And so the imbalance felt by Jupiter becomes weaker. And that's why the planets can just stop migrating and not migrate out, because Saturn, the imbalance on Jupiter is weaker, and so Saturn can counteract. So let's wrap up. It's almost the end. So a few takeaway points. So small planets don't change the radial surface density of the disk, but nevertheless break its axial symmetry by generating a spiral density wave. And the torque exerted by the wave forces the planet to migrate inward. This is the key of type 1 migration. So type 1 migration is proportional, as a speed proportional to the mass of the planet and the density of the disk, and it's inversely proportional to the square of the disk aspect ratio. And the disk also dampens the planet eccentricity on a much faster time scale, inversely proportional to the aspect ratio to the power 4, not 2. And the conservation of angular momentum tells you that when the eccentricity is damped, the semi-major axis is damped as well at the rate of the eccentricity damping rate, this rate, which overcomes the normal migration rate until the eccentricity becomes 0, then again at the normal migration rate. The co-orbital torque can block type 1 migration in where the disk has a steep surface density distribution, I deleted. So typically the inner edge of the disk or the outer edge of the gap. And it also acts to slow down migrating planets, but only if the disk has a low viscosity and a shallow surface density gradient, shallow than 1/2 to the power 3 half. So this is for the small planet. The giant planets open gaps in the surface density of the disk, and then they are trapped in their own gap. And so they have to move with their gap at approximately viscous speed unless the disk has a little mass, and this is the essence of type 2 migration. And two giant planets with a mass ratio comparable to Jupiter and Saturn, once in resonance, can halt or reverse their migration. And this is very important because, of course, Jupiter and Saturn exist in the solar system, so this is what they probably did. And we see this elsewhere, like for instance, the only two planets which are imaged in the disk, or like PDS-70b, PDS-70c, are in a sort of Jupiter-Saturn mass ratio, and they are in the 2-to-1 resonance. And indeed, people who tried to take the observed surface density distribution and simulate the evolution of the planet show that the planets don't migrate. So this is a very important point for giant planet migration. So we stop here, and I'm happy to take any of your questions. Yes. Not in these ones. There are simulations that put the planets off plane, but I did not mention any because time. So in principle, the Z evolution and the rest are decoupled. So if a planet is inclined, it starts to launch bending waves in the disk, and that sort of warp the disk. And these waves damp the inclination of the planet as the epicyclic waves damp the eccentricity of the planet. So the planet tend to go back to the midplane of the disk. And there are formulae, for example, Creswell and Nelson and so on, about the damping rate of the inclination. And then, of course, as long as the planet remains inclined, there is a feedback on migration, a little bit like the feedback of the eccentricity of migration before the eccentricity is completely damped. Again, there are factors in the formula. You can check the paper by Creswell and Nelson. It's the most updated paper. There is also a recent paper, I don't know what it's, maybe only for the eccentricity, like Pichieri et al. Also revised works of eccentric and I think also inclined planets. It's not very explored because, yeah, the inclination damping being so fast, typically one can consider planets to be coplanar with the disk, and then it's harder to excite the inclination of a planet. The eccentricity of the planet can be excited by resonances, as we will see tomorrow, those encounter with planet. Inclination is much harder once the system is coplanar. So there is much less rich literature on it. Yes. Yeah, sure. So these were example simulations. So the planet was fixed, except in the few where the mass was changed artificially to see gap opening and this kind of stuff. It was not done in a physical manner. Of course, the planets can accrete. So the Hill sphere of the planet is a field of gas, and so the planet can capture part of that gas and grow. So as a function of this, the Hill sphere get emptied and can be refilled by new gas coming into the Hill sphere, and the mass of the planet changes. So then it can open gaps, or it can strengthen its wave. There are also effects that I didn't have the time to talk about. It's about the fact that the planet that accretes gas heats up, and so it generates what is called the thermal torque. This was studied by Benitez, Lambe, and Massé, and others initially in a Nature paper, and then there is a number of papers on this effect. And so basically a planet that is very hot because it's accreting either solid or gas, heats the disk around it, and this changes because of the equation of perfect gases, the density of the gas is hotter, and with this changes the torque balance. Maybe this is what you alluded to. And yeah, these are the thermal effects in the disks. Is something I do not have the time to cover. They're more subtle. And here, all the disks I considered were locally isothermal. I think in general, there's been a lot of hope in these thermal torques to block planet migration. At the end, this is just temporary effects. So I decided these were not so important to be put in the first lecture. No, not really, because I mean, in my pressure gradient formula, I mean, the radial change in temperature is included. When we say that the scale height of the disk is a function of R, in R, this includes temperature decaying like 1/R. And so the gradient of temperature in the disk was included there. The fact that there is grains change of composition does not impact migration. Now, what can change with the disk is the opacity and the cooling grades. So how appropriate is the isothermal approximation? Then again, we go into this issue of thermally driven torques that I did not mention. I'm sorry. And so locally, these torques can be important, right? We're close to an opacity transition when you have a steep drop in temperature with the radius of the disk. You can have a co-orbital torque driven by the temperature gradient that excites and stops the planet temporarily. But these processes are very temporary, and they disappear. So I had to make a choice. But there is indeed a literature about these thermal torques, paper by Bertrand Beach. Bertrand Beach will speak later this week remotely, so maybe we'll mention those. Yeah, that I did not see. But they don't really change the overall picture. Inside everything that is important. Yeah, we'll start with it. Or maybe you choose. Both will speak. Migration by planetesimals and stuff. No. Planet engulfs into the star. We don't know. It depends how the disk ends close to the star. Right? If the disk was a continuous entity to the star, then the planet would go into the star. But it's close enough to the star, the disk is super hot, so it becomes viscous. It becomes ionized. So if it is ionized with the interaction of the magnetic field, it becomes strongly turbulent, so strongly viscous. This tends to create a drop in the surface density. And then even closer to the star, there is a so-called magnetic truncation. It's a second edge of the disk, where this co-rotation can actually stop the planet. And that's why we think there are so many hot planets. Because that's why they're all really fallen on the star. We should find just a few lucky ones. That is the last of the Moluccas. This was the first idea. But there are too many, so clearly they are not the last of the Moluccas. So in most cases, they stop because probably of the collocation torque, or if they are big enough, they open their own cavity, they go outside of the disk. And then there is also the tidal effect of the star. At some point, push the planet out, counterbalance. And there is something we did not ask, but is understood. There is also the question about the balance between gas-driven migration and planetesimal-driven migration. If this has planetesimals, and the planet is migrating to the disk, is migrating also through the planetesimal disk that act on the planet and can counteract a little bit. As long as there is a significant amount of gas, the gas migration wins, but then eventually planetesimal migration can take over. And I hope I will have time to talk a little bit about that. Well, the outer boundary is more evanescent, is the distant disk, is probably set by external photoevaporation in the disk. Can planets exist so close to the outer boundary? Can they go there? There is this tendency to move in. So don't expect really to see planets at the outer boundary. Not really, because type 2 migration follows the viscous evolution of the disk. And the disk is an accretion disk, so it tends to go inward as well, except in the very outer part. So this is what you may allude to with your question. The standard viscous evolution theory of the gas, this is a radius, this is sigma. You start with, you know, a narrow disk, it can be something like this. And then because of viscous evolution, the disk tends to spread like this. And until it cannot spread anymore because you have external photoevaporation. It may lose all the gas to go beyond the given. So in this kind of evolution, there is at each time, so this is increasing times, 0, 1, 2, 3. At each time, there is a distance that separates the disk in two. Inwards, the motion of the gas is inward, and outward of this distance, the motion of the gas is outward. So if you have a giant planet opening a gap here, it will move outward. But it has to be very close to the outer disk to move out. But as time goes on, the location of this point also moves. And most of the disk becomes accretional. So it's likely that even a planet temporarily going out eventually finds itself in the accretion part of the disk and start to move in again. So the outward type 2 migration is typically a temporary effect. not a sustained effect. If we have time, I'm happy to go on. This is flashing. Chairman, what should we do? Okay. 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 Yeah, migration is inevitable. Ah. Yes. Oh, yes. Well, I see first there can be an effect of distruncation. So if you truncate the disk, all of a sudden your disk will want to spread again vigorously out. So maybe this can help in trapping a giant planet in the expanding phase of the disk. And these things can all happen. I think they are not generic, but can happen. The flyby will also probably excite the orbit of the planet, making it eccentric, inclined to these two. So everything becomes messy until certainly the flyby goes away. But eventually, the viscous forces in the disk redamp the disk to a new disk, and the eccentricity, the inclinations are damped, and things should come back to normal. In a cold disk, yeah, very small. What part of the talk? Outward, yeah. So because it's dominated by the wave that Jupiter exerts in the inner disk, because of the partial gap opened by Saturn that imbalances the surface density distribution that the gas in the Jupiter sees. So it sees an inner disk close to Jupiter. The outer disk is partially depleted by Saturn. So the inner wave of Jupiter in the inner disk pushes the planet out, and because there is the gas freely passing through the gap, the planets are not blocked in the gap, so they can go upstream against the disk. This is the only case of sustained outward migration, because all the rest is temporal. Well, they are inside, so if they are already in resonance, it's the same, because the final resultant method. If they are closer than the 3-2, they become unstable. They are too close to each other. So by scattering, they separate, and then they migrate back towards a common resonance. Cannot be necessarily the 2-2, can also be the 2-1. It depends on the migration rate of Saturn, from the density of the disk and its surface density. So it could also be the 2-1. In normal viscous disks, it's 3-2. In low viscosity disks, it's more 2-1. If the planets are more massive, like PDS 70b and 70c, definitely 2-1. And if the planets are born closer, as they grow, they become unstable, they separate on eccentric orbits, the eccentricities are damped, they go back to circular orbits in the disk, they migrate again together until they find their resonance. We will see that tomorrow, but the resonance state is the only stable relative configuration in the disk. So whatever mess happens, unless a collision occurs, one planet disappears, and the planets find a way to go in a resonance.